I stall at the beginning because I want to give as many people the chance to get in here. Tonight we're going to be talking about empirical formulas. We're not going to be calculating density, so just be ready to not calculate density for the first time this term. So we are going to be looking at discovering using mass what the formula of a molecule is at the atomic level. So this is some really powerful techniques that can be used in the chemistry lab to kind of get something that is unknown and discover something about it at the atomic level. So let's just dive in with a story, because I like to start with a story if I can about the crazy past of science. But there was this ancient belief that every material contained this substance, phlostogen. Spoiler alert, it's not real. And that this phlostogen within the material was what gave it its combustion property. So materials with more phlostogen would combust in a greater extent to those with less. So this was kind of coined by the Greeks, and it wasn't until this scientist, Lavoisier, his French scientist, he had a real problem with this, because what people commonly knew the problem with this theory was that when you combust metals, they're supposed to lose their phlostogen, but then the resultant product of the burnt metal has more weight. So how do you lose something and gain weight simultaneously? So Lavoisier is known as one of the first scientists to kind of do experiments using the scientific method. He approached this problem systematically, and so we still coin him as maybe the father of the scientific method. So we'll kind of look at it as an experiment. See, he made these observations about metal burning, and it forms this substance that they used to call calx, which weighed more than the metal. And of course, if this is losing phlostogen, then why is it gaining weight? So his hypothesis was, well, phlostogen doesn't exist. Combustion is caused by something else, probably concerning air. So he did a series of experiments with mercury as his metal. And so at first he heated the mercury calx. So that's after it's been burned and it weighs more. And it decomposed into two products, a metal, the original metal, and a gas. And when he measured the mass of both of those, they equaled the starting mass of the calx. He heated plain mercury with that gas that he got from the calx, and it reformed the calx. And again, the total mass was the same as the reactants. He heated mercury in a measured volume of air, and he was able to get a measured volume of air remaining and some calx. And then when he took that remaining air and lit a candle in it, it quickly went out. So there was something that was happening with the air around this process. And so the conclusions were that he is also going to have discovered oxygen. So he said that oxygen, a normal component of air, combines with a substance when it burns. In a closed container, a combustible substance stops burning when it runs out of oxygen. And that the metal calx, and from this point forward, we'll refer to it as a metal oxide, weighs more than the metal because it includes the mass of the metal and it includes the mass of the oxygen. So this is his generalized and unbalanced idea, which is that metal M, some general M, added with O2 gas will make some metal oxide, but we don't know how many atoms of the metal or atoms of the oxygen are present in that solid. So this is a generic formula. And I want to just remind everybody, I know that you know this, but the law of mass conservation says that because atoms are never created or destroyed, they're just converted, that a chemical reaction can't result in a different mass of the products as long as all of the products and reactants are conserved, so no gas is escaping, then they have to have the same mass at the beginning and at the end. And that's really critical, both with Lavoisier's experiment and what we're going to do today. So I wanted to do an example of an empirical formula determination. I know that you've done this in class and that you had the master showing you, but I want to remind everybody in case it's unclear, because this is just going to be absolutely critical for what you're doing tonight. So let's say that we heated 10.000 grams of iron in a crucible and measured 14.298 grams of some metal oxide was produced. Determine the metal oxide empirical formula. So this is the kind of data that we're going to be looking at tonight, and this is what we're going to do with it. So let's jump in. So let's say that we have 10 grams of iron. Let's find out the moles. So we're chemists, we always work in moles, so 55.58 grams, 0.85, off to a bad start. Don't worry, I have an eraser. 0.85 grams in every 1 mole of iron. And so we get from that 0, come on, that's supposed to be a 0. Moles of iron. And now, how much oxygen do we have? Well, we start with the metal oxide mass, so that's 14.298. And that is some combination of iron and oxygen, minus what we know how much iron was in, and we can't lose any mass of iron because of the conservation of mass law. So that's 10 grams of iron, so that we know there was 4.298. Sorry, sometimes my pen has a little delay in it. Grams of oxygen. So now we have the masses of each element, and we need to know the moles, convert each mass to moles. So we have already the moles of iron because I jumped the gun. I'm always working in moles as a chemist, but we'll just jump over here. So now we're just going to look at the atomic mass of a single oxygen because we're looking at just the number, the mass that relates to this oxygen within the species. We're not looking at it as its elemental form O2. So it's only 16 grams for every 1 mole of O. And that gets us 0.26, oof, come on, sorry, technology, moles of O. So now we have each mole, so we can write our preliminary formula. So we'll put Fe 0.179, O 0.269. And then we'll divide each subscript by the smallest subscript. So 0.179, 0.179. And what we get to then is Fe. And I'm going to write, normally if it's 1, you don't include it. But just for right now, I'm going to show that there's 1 Fe and there's 1.5 O's. And so then, if necessary, multiply each subscript by the smallest number, the smallest integer, which turns each subscript into integers. So the smallest number would be 2, and 2 times 1.5 is 3. So that would turn everything into single integers. So we can go times 2. And so our empirical formula is Fe2O3. And because iron is a transition metal, we don't necessarily know what its oxidation state is. This isn't a given. And so here we see that we have iron 3 oxide. And so then we're able to put together our complete combustion reaction with this and balance it. So that is our goal tonight, is to determine this empirical formula for our metals and then create a balanced equation once we have the empirical formula. So we can jump into our software like we normally do. Hopefully everybody has access and is familiar at this point. We're doing experiment 4, the empirical formula of some copper oxide. And I want to remind everybody that we don't know the oxidation state of copper. So we don't know the empirical formula just from that name. It's copper something oxide. So we're going to make sure that we read the background material. There's not much there to read, but I want to make sure that everybody takes a look at it before we get started. That's going to help answer a lot of questions and jump into the procedure. And like always, I think the best option is to open it in a new tab or a new window so that you can see the procedure, you can see the lab. And I do recommend, if you're working with a group and they they like the idea, one person sharing the screen and kind of being the guinea pig, and I think it's a lot easier to follow along when you can visualize and you can talk and see the same experimental setup. So consider that when you're working with your groups. So our first experiment, and I'm going to do things a little bit differently tonight because we're dealing with a few new concepts. So at the beginning, there's two experiments, two parts to tonight's lab. And so I'm going to kind of give the setup of what we're hoping to achieve in unbalanced reactions. So please note that. And then at the end, before we move on to the second part, and before we move on to the post-lab information, I'll kind of give a plan of what data we're collecting and what we're going to do with it. So I really recommend, if you feel a little unsure about empirical formulas or doing these labs, what I recommend is making sure that you take careful notes because they're going to help you know what to do with the data once you've collected it. So we're going to start by making copper something oxide from copper solid by heating it in excess oxygen to make CuXOY. So we'll start with our crucible, that's this little guy, and put it on the bench, and we'll need a balance because we're working with masses tonight, of course. And we're going to add 10 grams of copper to our crucible, as we do. And we're going to be heating it using the Bunsen burner setup that we worked with last week for the boiling point and melting point determinations. So you're going to just move a Bunsen burner and set it to the medium heat. So feel free to play with the low, medium, high heats. So there's 4 settings: low, medium, high, off. And make sure that it's that blue flame, that middle flame. And then drag your, once you've confirmed the mass, of course, it's a digital lab. So of course you have exactly 10 grams because you said it has 10 grams. But you would want to make sure and confirm that you know the mass going in. And then you would drag it over your Bunsen burner and it will look like this. You want to visually see when the procedure is done. There's going to be a color change when the reaction is finished, and you want to observe that and then allow maybe 30 seconds more reacting time before you stop it. So we can't see this in this way. So if you double click on the crucible, you have some options here and it says show material and container. So make sure that you click this button right away so that you can see into the crucible like this. Once it changes color and you wait that 30 seconds, then we need to get a final mass, but before we can put it on the balance, it has to cool. And this will be true in face-to-face labs when we all re-enter society and we're back in labs. We can't ever put anything hot on our balance. So, and this software won't let you either. So maybe about a minute, it will cool down. If you can try it and it will just say it's too hot still. And you have to just wait until it's cool. But about a minute, that's fine. And then you can drag it onto the balance and get a final mass. And so that's then the mass of our copper oxide and the crucible. So then our plan, this is what we're going to do with the data. We're going to take that known mass of copper and we're going to convert it to the moles of copper. We're going to take that known mass of copper oxide, and that's calculated by difference in mass between the empty crucible and the crucible with the copper oxide. We can subtract the known mass of copper, and like I did earlier, that'll give us the mass of the oxygen. Then with that mass of oxygen, we can go to moles of oxygen, and now we have moles of copper and moles of oxygen. And so we can do the empirical formula procedure as shown earlier to find the empirical formula and the oxidation state of copper in this copper something oxide. So that is the first part of tonight's lab. And so experiment 2, we're doing a very similar thing, but we're going to get copper from a solution this time, not from its elemental form, its metal form. So there's a few extra steps, but we're still accomplishing or hoping to accomplish the same thing, which is oxidizing copper and determining its oxidation state through its empirical formula. So this is experiment 2. Here's what we're going to be doing. So this is kind of, so to speak, we're going to be taking solid copper sulfate pentahydrate, solid, and dissolving it in solution. I have 1 water here. This is really, you can think of it as infinite waters, and then this would be infinite plus 1, but the idea, or infinite plus 5. The idea here is that when you put your copper 2 sulfate pentahydrate into solution, once it's in solution, then we're looking at copper 2 sulfate, and the hydrate molecules are then just part of the water solution. So I wanted to say this because this can be a sticking point for some students. If this seems obvious to you, don't Don't overthink it. I just want people to understand that once it's in solution, these hydrate molecules go away. But for figuring out the moles of this original solid that we put in, we need to account for these 5 water molecules, and at 18 grams per mole each, that's kind of a lot of addition. So make sure that you know this is what we're starting with, and we're going to put it into solution. Then after that, we're going to take our copper 2 sulfate in solution and react it with NaOH. This is an unbalanced reaction, and that, based on our solubility rules, should yield copper 2 hydroxide and some aqueous sodium sulfate. And with our copper 2 hydroxide, we can take that out of solution because it's a solid. And then we are going to combust that in with oxygen. We're going to drive off that hydroxide as water. And what will be yielded with is copper X oxygen O, some copper oxide, and we can determine the empirical formula. So that's our plan of action. We're going to go from a solid on our bench into solution, from solution using solubility rules to a solid, and then our solid with oxygen to some metal oxide. So we're going to start this time with a balance and a 250 ml beaker. I missed one screen grab here, but we're going to add 25 grams, it's in your procedure, of the copper 2 sulfate pentahydrate. And then to that, there's a little bit of solid in there. We're going to add water, of course, to make our solution, 150 mils. And then to that, we're going to add our sodium hydroxide. This is 6 molar sodium hydroxide, and we're going to add 50 mils of it. So all within your procedure. So just drag and drop. And it's going to ask you to make sure that you record what evidence you see of the reaction. And all of this, of course, you're going to need for the post lab. So make sure that you're taking careful notes, but record whatever you observe. And then we're going to need another beaker, because now what we're hoping to do is take the solid at the bottom of our original solution, the beaker that we're seeing on the screen, and we want to combust that in excess oxygen to get the metal oxide. But right now it's in solution. So what we want to do is we want to decant. And in chemistry, what decant means is just to pour off the liquid in a solution that has a solid in it. So just to pour off the liquid. And some of you might have heard of a wine decanter, which is a piece of glass that you pour the wine into, and I guess it adds air and flavor. I'm not exactly a wine guy, but the idea is that you're pouring off. And so you're going to drag and drop your beaker into the clean new beaker, and you're going to click the decant button. Don't click pour all or any amount to dispense. You want to decant, and that's going to tell the computer to pour off the liquid and leave the solid. And so now we have 2 beakers, one with the liquid and one with the solid in it. So we're going to use a large test tube for our combustion. So first we're going to gather a mass of our test tube and put it on our workbench, and then transfer our solid, and easily enough we can just say pour all and it will transfer. If we were working in a lab, this would be a little bit more of a challenge. We would be using a spatula, and this would be a place where you would find a lot of loss and error, because things are going to be left. You're going to lose some when you decant, and then you're probably going to lose some in this transfer. And so when you have less than you expect at the end, that's often where it goes. So we would do this really carefully, but with a computer simulation, we can just click a button and transfer everything. So our numbers will work out really well tonight. So we'll pour all. And now we have our blue solid in our test tube, and we can bring a Bunsen burner down, and we're going to set it over the Bunsen burner on medium heat again until it changes colors. Again, we'll wait about 30 more seconds, and then we'll take it off to cool. Once our test tube has cooled enough to get a mass, we can get a mass, and we can subtract that from our original mass of the empty test tube to find out the mass of our metal oxide, our copper something oxide. And of course, we need to dispose of the waste. And in this case, this is important to dispose correctly. So we dispense in the waste container before we leave for the day. Okay, here's the plan of what we're doing. And so this is where it can get a little bit tricky. So I want to make sure that this is clear. We're going to take that original mass of copper 2 sulfate pentahydrate in grams and convert it to moles of copper 2 sulfate pentahydrate in moles. And from that, with the mole ratio, we can figure out how many moles of copper we started with. And that's what we really care about at the end. So from the moles of copper, now we can backtrack using the molar mass to find out what mass of copper was originally there. There's a few other ways that you can do this using techniques from your class, like mass percent. And so if you have a different way that you feel pretty confident that you can get the mass of copper, feel free to talk with your instructor or just go for it. But this is, I think, a pretty straightforward way, and I love to work in moles. So I say go to moles, do mole conversion, and then find the original mass of copper. Then we can take that mass of copper oxide that we got from the test tube and subtract the mass of copper that we added originally to get the mass of oxygen. And now we're pretty much home free. The mass of oxygen, we can figure out the moles of oxygen. And now that we know the moles of copper and oxygen, we can find the empirical formula of copper oxide, copper something oxide, with the technique shown before. So again, we're starting with the mass that we originally put in and converting to moles, and not forgetting about this 5 hydrate molecules to get the moles that we originally added, to find the moles of copper. There's 1 mole of copper in every 1 mole of copper 2 sulfate pentahydrate. From there, we can find the mass of copper. And then from the mass of the copper oxide, subtracting the mass of copper, we can get the mass of oxygen. So that's going to be the part, I think, if there is a part tonight that's a little bit tricky, it's right here. I think just be really, feel really confident in this is a tricky part. So if you're a little confused, ask your instructor, and we can make it as clear as possible. So, but then making sure you know what you're doing with the empirical formula will be critical, because after both experimental steps, we're going to be doing that empirical formula analysis. And then we'll jump into the post lab. So it'll look something like this. We're going to be putting in the data, the mass of the crucible. Make sure that you're adding in the correct number of significant figures. Even if you say 25 grams, we have a balance that has 3 decimal points. So what you're really adding is 25.000 grams. So remember that in that original analysis of the iron oxide example I showed you, I didn't say 10 grams, I said 10.000 grams. So that's important to make sure your significant figures are correct. And you can see that it's looking for color and things like that. So make sure that you're taking good notes so that you're able to just breeze through this. And then you're going to be putting in the balanced equation. So you have to have the empirical formula. Once you have the empirical formula, then you can use that to balance your equation. And you'll do that for both parts, putting in the data and the balanced equation for parts 1 and parts 2. And then there's a few multiple choice questions about nomenclature and just some of the conceptual aspects of tonight. And that's it, 13 questions, no graphs. It's a pretty straightforward and fun lab. I did it this weekend and I really enjoyed it. So let's get at it. Let's look at it like le voici. Are there any questions?
I just have a quick clarification question.
Yeah, what's up?
Do you mind repeating what you had said regarding the copper sulfate pentahydrates, like why it's like the tricky, like pay attention?
I think that, and maybe it's not tricky. I'm always looking for the thing that might stump a student in the analysis, especially if somebody is doing the analysis away. We have to determine how much the mass of the copper and the moles of the copper we originally started with. But we're going to enter it into the system as copper 2 sulfate pentahydrate. And we're only going to originally measure the mass of the copper 2 sulfate pentahydrate. But we can't use that mass for anything, because that's the mass of copper and sulfur and oxygen and water molecules that will not play a part in the later combustion. So we really need to know just how much copper is there. So there's a few ways of doing that with the mass percent, as I mentioned, but then you'd still have to find the complete molecular mass and the mass of copper, and I think that it's just as much work. So I think that you should go to moles and then use the mole ratio 1:1 to figure out how many moles of copper. And then you can backtrack with the molar mass to get back to mass of copper. And I'm just trying to overemphasize this because this is a fun and pretty easy lab. And so I think my job is to try to find any place where a student might struggle and make sure that I identify that first. So it'll be interesting to get feedback tonight from my students like yourself. If it isn't so difficult, then I won't belabor the point. But this is the plan, and I wanted to put this plan out so that people can kind of visualize what they're doing with the data. Yeah, because it can be kind of a lot, and at the end of it, you have a lot of numbers, but you need to be able to know what to do. Yeah, Brett, you have a question?
Yeah, I have a quick question. So this is kind of a side question about the future labs we're going to be doing. It doesn't seem like there's one scheduled for next week. It jumps from like 4 to 7, and I was looking at the due dates. Maybe I missed the due date. I just want to know if we were taking like a small break or something after this week. Maybe I misread the dates.
Janice, do you know which experiment is next week?
It's chemical reactions.
Oh, it's the first video lab.
Yeah.
Okay. So format will be changing a little bit next week. So we won't be doing a simulation. We will be doing a video-based lab, which was, so basically pre-recorded data. The same thing that we're essentially doing now. There'll be a pre-lab. It'll be on Canvas. We'll send an announcement out to make sure that everybody is right up to date with this. And then we'll have a pre-lab lecture just like we did, explaining what we need to know to be successful. And then in your groups, you'll watch a small video where the data is being collected and make your observations, and then do the analysis, the post-lab analysis as a group or on your own time. So it'll be very similar in theory, but we wanted to have a few experiments in where we could impart a little bit of real error, because unfortunately there's very little error in these. Everything weighs the same and just works out perfectly. So some of the labs we tried to shake it up. So it will be different in structure, but the pre-lab will be found on Canvas. We'll send an announcement out to everybody to make sure everyone's aware. And the functional way that you spend your week will be the same. So if you're asynchronous, you'll do it asynchronously, synchronously. We'll be with the group and we'll just figure it out. So a little bit different, but look for news coming out on that in the next day or so, okay? Any other questions?
I have a question.
Yeah. So just speak up. I have a hard time finding the faces or the hands up. Yeah.
Yeah, can you hear me now?
Yeah, go ahead.
I was just wondering, are we gonna have a pre-lab activity like we have in the Hidden McNeil?
Actually, you know what? There is no pre-lab for this one. Next week there'll be no pre-lab.
Yeah, because for the ones, I mean, I can see the ones. It was 2, 3, and 4 Hidden McNeil, and then it jumps to 7 or something like that. So I didn't.
Yeah. So right. So hey, we're gonna go off Hayden McNeil. Look for instructions coming out on this, but we are going to have, and we talked about this in the first lecture, but we're not just doing simulations. There's going to be some video labs, which we've pushed off. Most of the video labs will have a pre-lab element. But for this lab, we're going to be just going through a bunch of chemical reactions. We're going to do a lot of balanced reactions. It's kind of a lot of work. So I didn't want to just give more busy work to students who are already extremely busy and taxed. The other 2 video labs that we have will have pre-lab information. You're just going to bring your information that you know about chemical reactions. We're going to observe some chemical reactions, identify them, balance the reactions, get the net ionic equations, the total ionic equations. We'll have some fun learning about different chemical reactions, but there won't be a pre-lab for this.
Okay, thank you.
Mm-hmm. Anyone else?
But you will have a pre-lab lecture, just no pre-lab assignment.
Thank you. Yes. And hopefully that was understood, but if it wasn't, that's absolutely right. There will be a pre-lab lecture, and it will be pretty critical, I think, for this lab. We're going to be talking about different types of reactions and how to identify them. And I think if you aren't comfortable with that, this lab could be pretty challenging. Or not this lab, next lab. We're talking next week. But we'll have hopefully a nice, strong pre-lab lecture, and we'll all feel confident going into it. Any other questions? I know this is scheduled for an hour, but I just really don't have more to say. I think we're all becoming pros with this software. I'm going to stick around here to answer questions. I think that's where I'll probably leave it if there's no more questions. Oh, Alexander, you have a question?